Hi everyone, welcome back. So in today's video we are going to talk about something which is very interesting and also which is most frequently asked in interviews when you attend to interviews related to verification domain. That question is how to avoid race around condition in Verilog, system Verilog or UVM when you are modeling RTL as well as test bench codes. So you'll encounter this race around condition in both your RTL and testament codes while you are writing the Verilog, while you are writing it in Verilog as well as system Verilog or UVM also. So we will see in today's video how many ways there are there in this particular Verilog, system Verilog and UVM in order to avoid this race around condition. So I think you already know about what is race around condition. So okay, let's just me give a simple example for this. So basically when you are writing something into the memory, okay, and when you are writing some data into the memory location, and from that same memory location if the reading operation is also done, that means on a same memory location if both read and write operations are done, then that leads to race around condition. Okay, so hope you got what is race around condition. Now let us discuss what are the ways in order to avoid this race around condition when you are modeling RTL as well as testament codes in Verilog, System Verilog and UVM. Right. So before getting into today's video, if you are new to this channel, consider subscribing this channel and hit on the notification bell also. And also please do follow me on LinkedIn and Instagram also, where I'll be uploading posts related to Verilog system, Verilog and UVM. And also you can join my Telegram channel where I'll be forwarding the posts that I encountered in my LinkedIn about the opportunities in VLSI domain and all. Okay, the link is in my description box. You can go there and check it out. And yeah, coming to today's video, so there are many ways in order to avoid this race around condition in Verilog, system Verilog and UVM. Let us see them one by one. So coming to first thing, which is Verilog. In Verilog, there are very limited options to do this to avoid this race around condition. So the first thing is by using the non-blocking assignments. Like by using non-blocking assignments, you can avoid the race around condition compared to that of blocking assignments. So basically what you will do in Verilog is when you are modeling combinational circuits, then you will be using the blocking assignments. When you are using the sequential circuits modeling, then you will be using the non-blocking assignments, which avoids this race around condition to some extent. And there is one other way, which is when you are modeling the test benches in Verilog, you can do that at negate of clock. So that in RTL, whenever you are modeling the RTL logic, you can, when you are doing it in the posage of clock, so that this will ensure there won't be any race around conditions between these two when you are doing the simulation. Right? There is this way in Verilog. Okay, hope you got it. Like one is by using non-blocking assignments and other is by modeling the test bench code in the negate of clock, so that RTL will be at posage and TB is at negate, so that there won't be any collision between these two RTL test benches. Okay, so these are the two ways in Verilog. Now coming to system Verilog. When it comes to system Verilog, there are many ways in order to avoid this race around condition. Why is it? Because you already know that SV has many enhanced features, and also the encounter of race around conditions is much more easily happen in SV, because SV, you already know that SV's test bench structure is very complex in nature, because you will be using SV for verification and for verification of complex circuits. So basically the test bench structure will be complex in nature, which is why there are many ways the race around conditions may occur. Similarly, due to the enhanced features of SC, there are many other ways also to avoid this race around condition in system Verilog. Right, the first one is by using the program block. Okay, you already know that this program block acts as a separator for DUT and TB. Why is it? Because while we are talking about the scheduling semantics, we have already discussed about this. Like the entire code which you are writing it in the program block, it will be executed in the reactive region. Okay, so basically the RTL execution will be done in the active region and the program block will be executed in the reactive region. So what happens, since there is a time gap between this active region and reactive region, this will avoid the race around condition, right? So one is by using the program block. So whenever you are writing the RTL code, you will be writing it in a module block, and when you are modeling the test bench, you can write it in the program block, so that there won't be any collision between the executions, right? This is one way. And the second is by using mod ports. Yes, since mod ports here will be providing the direction from DUT to TB. Like basically mod ports are used to tell the direction for ports, whether it is input or output or in out. So basically which direction the port is mentioned in the mod port. So basically, since you are mentioning the inputs and outputs direction in mod port from D, and also you will be using the mod port when the input is going from DUT to TB and the TB to DUT also, so there won't be any collision because you are mentioning the directions, like which is input direction and which is output direction. You are mentioning it clearly in the mod port by using the mod port. So that is why this will also avoid the race around condition in case of system Verilog. And the third thing is event regions. Okay, you have already talked about this in the scheduling semantics region. If you didn't see that video, I link that above. You can just click there and you can check that scheduling semantics after completing this video. Okay, so event regions, basically in Verilog you are having only four events, four regions for all the events to simulation, like active region, inactive region, non-blocking assignment, which is NBA region, postponed region. So basically in Verilog there are only these four regions, but when it comes to system Verilog there are a total of 12 regions where every event will be executed in its own region. For example, if you since we have discussed like program block, it will be executed in the reactive region, and assertions they will be executed in the observed region, right? And then non-blocking assignments they will be executed in the non-blocking assignments will be executed in the NBA region, and again non-blocking assignments within the program block they will be executed in the reactive NBA region. In this way every event is having its own region in which it will be executed. So because of these enhanced regions in this system Verilog, this will also avoid the race around condition within system Verilog. And then the next thing is by using the specify blocks. So basically specify blocks you will be seeing it in both system Verilog and Verilog also. It is nothing but a special construct which is used to define the timing characteristics, okay, and delays of the signal. Okay, it is used to specify the delays of the signal within the modules. So it will allow these designers to specify the delays across the modules, and it will also perform the timing checks like setup time and hold time checks. So all this it will be performed in the specify block. So in SV it will also ensure that the input satisfy the timing constraints. So basically if you're having any timing constraints, so it will by using this in the specify block, all this whether all the constraints are executed in the specific timing region or not, it will be specifying it. So basically by using specify blocks also you can avoid. So basically you will be seeing this keyword called spectrum. Okay, this will be included in this specify blocks. So by using the specify blocks also you can avoid the race around condition. And then the last thing is by using clocking blocks. So basically mod plots and clocking blocks both are like basically use mod plots is used to describe the direction of the port, whereas clocking block we know that it is used to provide the synchronization between DUT and TP. Okay, so clocking block is basically it is entirely based on the clock, okay, generating the clock, and it will also maintain the synchronization between the DUT clock, whereas test bench clock. Okay, and here we should also remember that clocking block execution should always be in synchronization with assertion evaluation. So basically, it will always be in synchronized with assertion, because you already know that assertions will be executed in the observed region, and then they output like which will be displayed whether the assertion is passed or failed. Again, it will be seen in the reactive region. So basically, the clocking block execution will be in synchronization with these assertion values, so that there won't be any race around condition occur because of this synchronization. Also, okay, so these are the things and about this particular system Verilog. So in this way, by using these many ways, you can avoid the race around condition in system Verilog, like by using program block, or by using mod points, by event regions, by specify blocks, and then by clocking blocks. Now coming to universal verification methodology. Okay, universal verification methodology, since you are whatever you are learning in system Verilog language, you are putting that into action in this universal verification methodology. And also, universal verification methodology is having some more enhancements compared to that of system Verilog. Like so in universal verification methodology, along with the things that we have discussed in system Verilog, what can more we use in universal verification methodology in order to avoid this? The first thing is by using UVM phases. You already know that you in UVM you will be having lots of phases like build phase, connect phase, etc, etc, etc. So basically, by using these phases, you can avoid the race around condition, because based on the phase the execution will be done. Okay, so which in connect phase some execution, some amount of execution will be done. In the build phase, some amount of building is building concept like execution will be done. You will be learning all these things when you go into UVM. If you already know about UVM concepts, then I think you can understand what I'm speaking about, right? And if you are not aware of UVM, you can just listen this and you can just remember this. And while I have starting the I'm going to start this UVM, then you can understand about these things. Okay, so by using the UVM phases. And the second thing is by synchronizing the UVM domain with the UVM phases. Okay, by using the domain and phases synchronized in nature, you can avoid this race around condition. And also by properly using the forward and backward jumps, also you can avoid this race around condition. And by using the user defined phases, and then use of starting phase, drain time, propagation mode. So these are various categories by which you can avoid the race around condition in universal verification methodology, right? So these are the ways in which you can avoid race around condition in Verilog, system Verilog, and UVM. Hope you like this video. If you like this video, please do like it, and also share this to all of VLSI aspirants who also want to enter into design and verification domain. That is all for today. Thank you all.